All right, this section here, you'll find there to be some rather nasty algebra and trigonometry involved. Although your knowledge of trigonometry won't be pushed to a lot of limits, just your knowledge of the identities. And it's not a lot of identities that are used. But let me start off with this integral. This is not a type of integral that we've dealt with before. That means, you probably find the answer in the back of the book if you look. I don't know. But this is not a form that we get, like, you know that this comes out to be arcsine or arctangent or one of those. It's not one of the ones we've had yet. So how do we work something like this? Well, before I begin this, I want you to think about something. First, x can be any real number. If you try to let u simply equal x, that will have the effect of changing the variable to u. That doesn't do anything for you. So, and that's really never a good substitution to use, u equals x. It doesn't do anything except rewrite the same problem. The reason why I bring up this, x can be any real number, is if I want to make some sort of a substitution, I have to make sure that what I'm using to substitute will be able to handle whatever x can possibly be. So, I say let tangent of theta be equal to x. Now this seems like a very strange thing to do, but no matter what x is, there is a theta for which the tangent of theta equals x. In fact, theta only has to go between negative pi over 2. You'll probably remember the graph of tangent does this. Kind of like a cubic, but not quite. It has vertical asymptotes at negative pi over 2, and it has a positive asymptote at pi over 2. What I'm saying is, if x is any possible real number, put it up here. These are thetas now, so I'm talking about a different system of reference anyways. But somewhere up here, or even y, it doesn't really matter. Whatever y is, or an x value up here, you can always go over and you'll hit the graph and you'll be able to find a theta that corresponds to it. In other words, what I'm really doing is allowing theta to equal the arctangent of x. We'll talk about that in a moment, but let me show you what it does to the integral. So, since the important thing is that tangent of theta takes all real numbers so that it can assume any value that x has to offer. So let's see what happens when I start this integral. Everywhere you see x, I'm going to start doing some changes. Now, if tangent of theta equals x, take the derivative of both sides of this, and you'll get secant squared of theta, d theta, equals dx. So I will replace that as well in the problem. So let's see what happens. 1 plus, now instead of x, I'm going to put tangent of theta, so we have tangent squared of theta. And then instead of dx, I'm going to have secant squared theta d theta. Now, when it comes to working these problems, we don't have limits of integration, so I don't really have numbers to go by. And you probably, or you should remember the identity that this quantity here is equal to secant squared of theta. All right, now what we should have next, this all depends on what values theta can assume. But for just getting a formula here, we can, since this quantity here is positive no matter what, the whole integral is positive, I should really, that's why this stuff, it's got to stay positive. We typically worry about the thetas and the other things if we had limits of integration. So right now I'm going to go ahead and ignore that, and I'll get secant cubed of theta d theta. Now this one itself has its own little particulars. Actually, you know what I should have done? So I'll ignore the absolute value for the time being. If I had limits of integration, I would do something different, depending on where they were, of course. I'm going to leave it in this form because now I'm going to do a partial, or integration by parts with u will equal secant theta, and then du equals secant theta tangent theta d theta. The purpose for choosing the u to be secant theta is because this piece right here, dv will equal this, would be very nice because its antiderivative is simply equal to tangent. So my dv equals secant squared theta d theta. I'll coordinate this off so it doesn't interfere with the problem. And so I end up with uv is secant theta tangent theta minus, now I need to do v du. You've seen this before. I'll end up with secant theta tangent squared theta d theta. And then we'll change this tangent to secant squared theta minus 1. I'm going to use the same identity I did before. Alright, let me multiply through a little bit. Well, this is really nice to have that secant cubed because I had on the other side a secant cubed. You'll see what I mean in a second. All right, now we have a formula for the integral of secant theta. What I'm going to do then is I'm going to add secant cubed theta to both sides. So on the left-hand side, I'll get 2 the integral secant cubed theta d theta. Over here, I will get secant theta tangent theta plus, now the formula for this is the natural log, absolute value of secant theta plus tangent theta. Since the integrals are all gone over here, I'll put a plus c. Now to get my final answer for this integral, I'll divide by 2. Of course, I'm reminding you of this. We did this problem before. All right, now we are in the world of thetas and trig functions. That's not the original problem. Was given e. We did know it. Raw to use. That's not so scary. But I see it's there right here. So I can convert my x's back to tangent, or tangent theta back to x's. So let's go ahead and throw those in. 1/2 secant theta. Tangent theta was equal to x. 1/2 ln secant theta plus x plus c. Now, we're close. The only problem with this answer is that it still has some thetas in there. I know the tangent of theta was x, but what about secant of theta? Now, since we don't know numbers for anything, we're going to just act like we're in the world of the best possible sense. That would be where everything is positive, including secant theta. What are we talking? Quadrant 1. If I had numbers to deal with, I would put my minuses or where I needed to put them if I had to. So here's what we know. We know that tangent of theta was equal to x, and indulge me for a moment while I call it x over 1. Then a good thing to make for yourself is a triangle here. Put your theta in the corner like you would for any other triangle, and then notice the tangent of theta is opposite over adjacent. That means I can have an x for opposite and a 1 for the adjacent. But then that makes this last side very simple. 1 plus x squared, the square root of that. Well, now I can work with secant of theta, because secant of theta is hypotenuse over adjacent. And I could clean up a little bit. I think I will just a teeny little bit. And it goes like this. If you go back to this integral, the square root of 1 plus x squared dx, instead of letting tangent of theta be x, another thing I could let be equal to x is I could let the hyperbolic sine of, let's say, t equals x. If you remember, the range of hyperbolic sine is negative infinity to infinity, so it could cover all possible x values. Then when I take the derivative, I'll get cosh of t dt will equal dx. Let's throw them in. So instead of an x, I'm going to replace it with a hyperbolic sine. And instead of a dx, I'll have a cosh t dt. The reason why this is such a good thing is because 1 plus hyperbolic sine squared is equal to hyperbolic cosine squared. And you don't have to worry about the absolute value of hyperbolic cosine, because cosine's range goes from 1 to infinity. Hyperbolic cosine goes from 1 to infinity. It's never negative. So this simply equals, this here then is just going to be cosh. Cosh times cosh is 2 cosh. Big gosh. I'll put the 2 here. I don't know why I said this. Cosh squared. Just like with trig functions, there's a half angle identity. You can rewrite this as 1 plus cosh of 2t over 2 dt. I'll take the 1/2 out front, and I'll have 1 plus cosh 2t dt. And I'll go ahead and rewrite it as 1/2. The integral of 1 is t plus, now remember this one, the antiderivative of cosh is a hyperbolic sine. Now because of this 2t, you're going to end up getting a 1/2 hyperbolic sine, but then there's a 1/2 here, which will make it a 1/4 hyperbolic sine of t, 2t. Put a constant. Well, this is nice because hyperbolic sine has a similar identity to regular sine, and that is 2 hyperbolic sine of t hyperbolic cosine of t. So I can make that into a 2, 1/2. Now let me go back and find out what t was equal to. T went too far. Right here it is. t equals arc hyperbolic sine of x. Now sine of t was equal to x. What is cosh of t? Well, remember, cosh of t, I'll write this, cosh squared of t equals 1 plus hyperbolic sine square of t. That means I can take that and change it to that. But hyperbolic sine was equal to x. If you want, you may leave your answer like that. I'll see if I can make this vinculum a little better. Oh, the whole thing goes. Or you could try to get something in there for hyperbolic sine. It doesn't look like we want, but you'll remember this. One of the formula for hyperbolic sine inverse of x was ln of x plus the square root of x squared plus 1. That was a formula for it. So I can write my final answer if I want to really. You could leave it like this, and you'd be done. But just to show you, we get the same answer as before. You can see that this answer matches up with what we had before. By the way, you may wonder, why is there no absolute value here? It's because no matter what, the positivity of this piece is greater than whatever negativity this might be. This is a little more than the absolute value of x. All right, so I started with an example that may or may not have been bad. The second iteration of it certainly was much nicer than the first. But this is the nature of these things. They get ugly quick. Try to integrate 1 over 16 plus x squared dx. And now, my mind, my inspiration, if you will, is this one. 1 over 1 plus x squared dx equals arctangent of x. That's my inspiration. This isn't quite there, but I can make it there by making and doing a substitution. What I'm going to do is, it sure would be nice if I also had a 16 in front of the x squared, because the reason why that would be nice is I could factor the 1/16th out front, and then I would have this thing over here. So how do we get that to happen? Well, one of the things we could do is I could let for u equal x. See, x can go from negative infinity to infinity. There's no restriction on x's. There's nothing even here that makes this denominator 0. But the function for u can be anything also. So I've got that covered. So I have for du equals dx. And we end up with the integral of 1 over 16 plus, now instead of an x, I'm going to put a 4u in its place. 4u squared. And instead of dx, I'll put 4u. 4du. And this will equal, I'll put the 4 out front, I'll put the du up here. I have 16 plus 16u squared. I'll pull the 16 out, so that out front we have a 1/4. And now I got what I want. 1 over 1 plus u squared du. And using the inspiration here, I have a u instead of an x. I don't think that's a big deal. I'll get 1/4 arctangent of u plus c. 1/4 arctangent of u plus c. But what was u? U was equal to, not 4u, u was equal to x over 4. So 1/4 arctangent of x over 4 plus c. So the real first example was not so bad. Here, I have no such inspiration as I did before. Now, if this were 1 over that, I would be thinking of arc sine, something like that. All of our trig stuff seems to have things in the denominator, all the stuff that we've memorized. So what I'm going to try then is to make this into a trig integral by making the following substitution. My inspiration, if I have a number minus t squared, I always look at this as my inspiration. Cosine squared of x equals 1 minus sine squared of x. The idea is this. If I could somehow make this into a 1 minus sine squared, then I'd have the square root, I'd have cosine squared under the square root, and they would cancel, and I'd be able to work with it. So this is my inspiration. The most seemingly reasonable thing to do would be to let sine of x equal t. The only problem with that is that if I put that in there, I'll get sine squared of t, but I'll have 36 minus 1 sine squared of t. I somehow need to get 36 minus 36 sine squared. I somehow seem to need to make that happen. So what I can do is this. Let 6 sine. I shouldn't have used x. That was a mistake. The reason why, there's nothing wrong with using x. I could do that. It's just your textbook will always use a theta, and they'll never use an x. So I don't want you to be thrown way off by that. So the substitution I'm going to use is this. 6 sine of theta will equal t. That way, when I plug it in here, I'll get 36 sine squared of theta, but the 36's I'll be able to factor out, and then I'll leave you with a 1 minus sine squared. Secondly, you ought to know for this that the lowest t can be as -6 and the highest t can be as +6. So t is allowed to roam between -6 and +6. Now it just so happens that sine of theta lives between -1 and 1. However, -6 is less than or equal to 6 sine of theta is less than or equal to 6. So what I'm saying is 6 sine of theta can take on whatever values t wants to happen. So we go back to the integral. The square root of 36 minus t squared dt. Square root of 36. Now t is being replaced by 6 sine of theta. So I'm going to get minus 36 sine squared of theta. And I didn't do a dt yet, but 6 cosine theta d theta equals dt. You could have let cosine of theta be equal to t, 6 cosine. However, when you took the derivative, it would give you a negative, and I don't want to. I try to keep things simple every single step. I don't want to introduce negatives if I don't have to, and things of that nature. So anyways, let me attach to the end of this 6 cosine of theta d theta. Now this 6 I'm going to pull out front. Now right here I'm going to pull out a 36. I should probably have just done this at once. You could have handled it, I think. If I take out a 36 from this, it'll come out as a 6, and this other 6 will give me the 36. So I have 1 minus sine squared of theta times cosine of theta d theta. That equals 36. 1 minus sine squared, of course, is cosine squared of theta. Now, cosine squared of theta typically is the absolute value of cosine of theta, but since I don't know any numbers, I am going to take the easiest route out of this and just think of it as cosine of theta. So that I'll have cosine of theta times a cosine of theta will be cosine squared of theta d theta. Now the only way we have of dealing with trig function squared like that is the one particular identity that goes 1 plus cosine of 2 theta divided by 2. I'll pull the 1/2 in front to give me an 18 integral 1 plus cosine of 2 theta. Now I'm ready for my integration. The antiderivative of 1 in this scene is theta. And then here, if you'll remember, you'll not just get sine of 2 theta, but because of this in here, you'll get 1/2 sine of 2 theta. And now you're ready to put your plus c because all integrals are gone. Now what I got to do is put it all back. The theta part is not a problem at all. Let's find out where theta would be. If I were to try to get theta alone here, let me write it. I would first divide by 6. So I would sine of theta would equal t over 6. And then theta would equal arc sine t over 6. So I'll get arc sine t over 6 plus, this is where I'm going to use the identity that this part equals 2 sine of theta cosine of theta. So I get sine of theta times cosine of theta. And now once again I'll throw on my sine of theta. And that was t over 6. The only thing is I don't have cosine of theta, so let's do that one. And once again I'll appeal to the triangle. Sine was t over 6, and sine is opposite over hypotenuse. And then cosine of theta then is adjacent over hypotenuse. You can clean up if you want to. I'm not sure that I see a real reason to. I probably put parentheses around that. I guess you could clean this piece up a little bit, instead write it over 36, whatever you need to do. But that is the correct answer. All right, for this one, I'm not sure if there's anything in the book. I think there's one that has like a t here, but maybe not a t squared. I'm not really sure. I don't really care if there was one way or another. But I see 9 minus t squared. In my mind, that's no different than this scenario. So what I'm going to do is the same kind of a deal. I'm going to let 3 sine of theta equals t. That way, when I square the 3, I'll be able to take the 9's out up there and be left with 1 minus sine squared, and I'm working. So we'll start with 3 sine of theta equals t. Make sure your ranges are permissible. T can go from -3 to -3. It can't go past 3 because that would make this negative inside of here. It can't go lower than -3 because that would make that negative inside of there. Sine goes from -1 to 1. The 3 on the front ensures that it goes from -3 to 3. Now let me differentiate. I get 3 cosine of theta d theta equals dt. Let's make my substitutions. Okay, so dt is 3 cosine of theta d theta. And in my denominator, t squared will be 9 sine squared of theta. And then the square roots, I'm going to get 9 minus 9 sine squared of theta. Alright, there is going to be a ton of simplifying that goes on here. Let's see. One thing I can do, I can divide out the 3 into this 9. So I have a 3 so far. But don't forget, when I pull this 9 out of here, I'll get another 3. So it looks to me like I'm going to have 1/9. We've got cosine of theta. I'll put the d theta at the end. It's in my way right now. Sine squared theta times 1 minus sine squared theta d theta. Of course, this right here will just be cosine squared and the square root of cosine squared theta is absolute value of cosine theta, but since I don't know any numbers, I'm just going to do cosine theta, d theta. Cosines cancel. This is the sine squared can be written as cosecant squared. And that, of course, is equal to negative 1/9 cotangent of theta plus c. Now let's go back to our original thing. What was sine? 3 sine of theta equal t. In other words, sine of theta equals t over 3. So now make the triangle. Put your theta there. Sine is opposite over hypotenuse. So there's my opposite, there's my hypotenuse. That forces the other side to be this. Now I can go back and change everything. Cotangent is equal to adjacent over opposite. Example 4 involves one that at first doesn't look like it belongs with some of our problems. It goes dx over the square root of 3 minus 2x minus x squared, the square root of all that. Now, in order to make use of our stuff, we typically need a number plus something squared or a number minus something squared or turned around or something like this. This has a third term, but we can fix that using completing the square, and I'll sort of remind you of what that is. Start in here. Typically, I'll rewrite this as negative x squared minus 2x plus 3. Now, the way you normally work this is you factor out whatever number is in front of the first, the leading coefficient, but you take it out of the first two terms. So in my case, I have a negative 1 in the first two terms. Now, I'll put this over here because my intention now is to add a number in here to make this into a perfect square. And if you remember, the thing to do is to add half of this squared. So what is half of 2? Well, that's 1. And if you square 1, it's still 1. But now be careful here. What you've in effect done by putting this right here is you've added a negative 1 to the whole expression. So to fix that, I'll put a plus 1 on the outside. This way I subtracted 1 and have added 1, and so everything's good again. Of course, that stuff factors as x plus 1 squared plus 4. So let me come back to my integral. And now I've not actually done anything, but now I have dx, other than rewrite it so it'd be easier to work with. Now, I'm thinking of something arctangent-y, or not arctangent, arcsine-like. So I could let 2 sine of theta equal this. If you know the arcsine formula directly, you can scoot your way out of it by doing this. I could let 2u equal x plus 1. There's no restriction on what x is allowed to be, nor is there any restriction on what u is allowed to be. So when I throw it in here, I'll get gx over square root of 4 minus, so in place of x plus 1, I will replace it with 2u. But then I've got to change the dx. I'll have 2 du will equal dx. So I can put a 2 out front there and du over here. And then we end up with 2. I'm going to factor that 4 out. And so now those 2's of course cancel. This is arcsine of u. And now what was u equal to? U actually equals x plus 1 over 2. Okay, now this one, I've tried to pull in something that has all the bells and whistles, and we'll see if maybe that'll work as a culminating problem. Ooh, x cubed dx. All right, let's see what happens here. I'm going to play the same game as before, and let's see. Here I have the variable squared minus the number. Now I don't want to do this then, like cosine squared of x, 1 minus sine squared of x. The reason I don't want to use this as my idea is because the variable part of it is after the minus, and here the constant part is after the minus. So I need the variable part to come first. Now I could multiply everything through by negative and then deal with a negative cosine squared, but that's not such a smart thing to do, I don't believe. Instead, I think we'll use this identity. It's the one that goes tangent squared. Let me use theta. Theta equals secant squared theta minus 1. That way, the variable part occurs before the minus sign. And let's check secant theta as a substitute. I need to get this to turn out to be something squared minus 1, which means I need this part, I need a 25 before the x squared, so I can take out the 25 when all is said and done. So, what I can do is this. I'll start with secant theta equals x. I'm giving myself some space because I might need to put some numbers in between things. Now if I tried, let me just play a little bit here. If I tried to put a 5 in front of the secant, then if I squared this, I would get a 25, which is nice. But there's a 9 there. Okay, now let's try this again. If I square this quantity, I'll get 25 over 9. 25 over 9, the 9's will cancel, and I'll have a 25 in front of my variable and a 25 after the minus sign. That's exactly what I want to have. Then I can go ahead and use an identity like this. So let me take the derivative of this. I get 5/3 secant theta tangent theta d theta equals, and this is really nice because this side is just dx. Alright, I'll make sure that everything works out. I'll put my 9, and I'll put this in parentheses and squared. 5/3 secant theta squared minus 25 all over, and the bottom was x cubed, so this thing cubed. 5/3 secant theta cubed. And then what did I have at the end? Dx was this stuff. Alrighty. That doesn't look like I'm going to get much on each. I'll just go line to line here and see what happens. Let me go ahead and square these. I'll do this in somewhat step-by-step detail. I'll have 9 times 25 over 9 secant squared theta minus 25. Down here, this will be 125 over 27 secant cubed theta, and then over here I'll have 5/3 secant theta tangent theta d theta. I don't think I'm going to simplify just yet. Let me flip things and make some other things work out. Those 9's will cancel, and as I mentioned, I'll be able to factor out the 25 and bring it out as a 5. So this is where I'll start putting it out front. So I got a 5 for that part. What would be left in there? Secant squared theta minus 1. Okay. When I deal with this part here, if I were to bring it out front, it's actually 27 over 125. And then I've got this 5/3 to deal with. All right, I noticed here I can take out one secant and make it a secant squared and take that out with it. So I'll have a secant squared, and then I'll have a tangent theta d theta. All right, let's do some canceling now. I'll take these 5's out, and that'll leave a 5 here. And then I'll take this 3 out, and that will leave a 9 here. So I get 9/5. And this thing isn't mentioned. This is tangent squared. So when I take the square root, I'll just get tangent. But there's a tangent out there waiting for it. So I'll put tangent squared over secant squared theta d theta. You may be tempted to let u be tangent of theta because then du would be secant squared of theta. But then the d theta would be stuck in the denominator also. So you're stuck with this. You can't do that. You can, if you want to make life easier on you, change this back using the formula for tangent squared. And tangent squared was secant squared theta minus 1. Then, if I break that fraction up, I'll get secant squared over secant squared minus 1 over secant squared. Well, 1 over secant is cosine. And then I'll have to do the thing that I always do, the double angle formula. Now, if I think of this as 1/2 minus cosine 2 theta over 2, I'll be able to take 1 minus the 1/2 will give me a 1/2. And now I'm ready to integrate. I'll get 9/5 times 1/2 theta minus 1/4 sine of 2 theta. I've done that enough to, I think I'll let you go back and look it up if you can't remember. I get 9/5 times 1/2. Now let's find out what our theta was. It's going to be arc something. Oh my, there it is. Secant of theta would have been 3/5. So we have arc secant x, and then I have I can use that one thing again to get minus 1/2 sine of theta cosine of theta. You know, I'm taking the 1/2 out of there. I'm tired of dealing with it in there, so I'm going to bring it out front to make this a 9/10. Cosine, if secant of theta, let me write it up here. I didn't do it. I shouldn't encourage going so fast here. Secant of theta equals 3x over 5. That means cosine of theta would be 5 over 3x. And then a sine of theta, well, what would that be? Well, I think it's a good idea to draw a triangle again. You knew that cosine of theta is 5 over 3x. Well, cosine of theta is also equal to adjacent over hypotenuse. And that forces this side to be 9x squared minus 25. You notice that's part of the original thing, and that always happens because of the nature of trig substitutions. So in this spot goes a 9x squared minus 25. Oops. Careful. All right, one last example will be an example involving definite integral. So we'll go with it. In this one, we'll go from 6 to 6 radical 3. We have z squared all over z squared plus 36 squared dz. Looking at something squared plus 36. Well, one of the identities that works really well with that, technically speaking, the hyperbolic ones work very well with this. I could let hyperbolic sine be z, and then you'd have, or 6 hyperbolic sine be z, and then I would have 36 hyperbolic sine squared plus 36. I'd be able to factor the 36 out. I would have hyperbolic cosecant, and, well, a lot of good things would happen. But most people won't go for that. They typically would go instead with probably a tangent right here, because tangent squared plus a number is a good thing. That'll give us a secant squared. In fact, what would be a good one to use? Well, 6 tangent of theta equals z would be a really good one to use. And then let me take the derivative. 6 secant squared theta d theta equals dz. So let's plug everything in and see what happens. First, I'm going to change these things. If I were to have z equals 6 radical 3, you'd have a 6 that I could cancel out. And it comes down to tangent of theta equals radical 3. Where, remember, when you're talking about arctangent, it operates from negative pi over 2 to pi over 2, which are the fourth and the first quadrants. If I'm dealing with positive numbers, I'm in the first quadrant, which is always the best place to be. But let me go back to this for a minute. If I did have a 6 radical 3 here, and you divide it by 6, the question then becomes, where is tangent of theta equal to radical 3? This is one of those ones you're supposed to have memorized. You probably have it memorized for sine and cosine, but maybe not tangent. So what I do in my mind is I think, where would radical 3 be the dominant place if I had sine on top and cosine in the denominator? Well, it would be dominant where sine is radical 3 over 2 and cosine is 1/2. Where is that equal to? Well, now you should know that that is pi over 3. Now, if, on the other hand, when I plug 6 in for z, I'll have tangent of theta is equal to 1. Well, where is theta then? Theta has to be pi over 4. Now let's plug these things into the problem itself. So instead of right here, I'm going to have 36 tangent squared of theta. Down here, the same thing, 36 tangent squared of theta. Plus 36 squared. And then I got to replace my dz with 6 secant squared theta d theta. All right, this will go from pi over 4 to pi over 3. Let me bring that 36 out there. Tangent squared of theta. I think I'll factor out a 36 from there too, so that'll be 36 squared times tangent squared theta plus 1 squared, and then I have a 6 out there, 6 secant squared theta d theta. There's a ton of canceling that can happen here right now. What I'm going to do first of all is I'm going to take out a 36 here with that one. And then I've still got this 6, so I'm going to cancel that into there. And all in all, this leaves me with 1 over 6 integral pi over 3 pi over 4 tangent squared of theta And then I have secant squared of theta, all in the numerator. In the denominator, this part is secant squared of theta, but then you're going to square it, so you're going to get secant to the fourth of theta, d theta. Well, it seems clear to me that we can cancel out a secant squared. I'll write it again just so no one gets confused. Tangent squared theta over secant squared theta d theta. Well, this is nice. We just happened to have done a problem that ended up like that. So let me pop back to there and see what we did. There it is right there. Tangent squared over secant squared. They did that. I just want to get to where what we used for the answer. Here was the answer right here. Let me grab that thing. And now I can just plug in the numbers directly. This is nice. You don't have to go back to x or anything like that. Now you're dealing with, these are theta values. I can just plug them right in here. I'll have 1/6 times 1/2 pi over 3 minus 1/4. What is sine of pi over 3 is radical 3 over 2. Sine of 2 pi over 3 is also radical 3 over 2. Now, if I plug in pi over 4 into 2 theta, I'll have sine of pi over 2, which is equal to 1. Let me go ahead and simplify in here and see what happens. Pi over 6 minus radical 3 over 8 minus 1/6 pi over 8 minus 1/4. So it looks like pi over 36 minus radical 3 over 48 minus pi over 48 plus 1 over 24. Well, everything goes into 144. So this goes in there 4 times. So I have 4 pi over 144 minus 3 radical 3 over 144 minus 3 pi over 144 plus, I think that goes in there 6 times, 6 over 144, and we end up with pi plus 6 minus 3 radical 3 all over 144. And I'll let you check the numerical approximation to that, but that's a good enough answer for me. So